In this video and our last video, we talked about inner products and norms. This is the overview slide for this video and last video. In the last video, we talked about dot product, inner product spaces, and properties of an inner product space. In this video, we will focus on norms and orthogonality. This is our overview slide, which we'll spend about 5 minutes going over before we do a very brief review of what we covered in the last video, and then we'll take a closer look at norms and orthogonality. We will start by reviewing the dot product for Rn from vector calculus, and then we'll move on to the inner product, which is an abstraction of the dot product. That is, these important properties of the dot product are preserved in the inner product, which we use on general vectors, not just Rn, but other vectors as well. So our inner product is a function that takes a pair of vectors and maps it to a number in our scalar field, and would denote the inner product with these angle brackets. So this is the inner product of u and v, and we will see that the properties here correspond to the properties of a dot product. We then define the inner product space, which is a vector space along with an inner product, and we had these properties of an inner product space. After we finish our review, we'll go on to our new material, including the norm. So a norm for a vector v in our vector space is denoted with these double bars, and it's defined as the square root of the inner product of the vector v with itself. Properties of the norm include that the norm of v is equal to 0 if and only if v is the 0 vector, and 2, we can pull out a scalar. So the norm of a scalar alpha times a vector v is equal to the absolute value of alpha times the norm of v. Next, we will talk about orthogonality, which you have probably seen some of in vector calculus. So when we have two vectors in our vector space, we call them orthogonal if their inner product is equal to 0. So in R2, we found that the inner product, and for the inner product we use the dot product for R2, is equal to the norm of u times the norm of v times cosine of theta. And so when are u and v then orthogonal? Well, that happens when cosine of theta is equal to 0, because we're considering u and v not to be non-zero vectors. So where is cosine of theta equal to 0? That's when theta is equal to 90. And that's where we have this idea that orthogonal vectors are perpendicular vectors, that they are at a 90-degree angle. We will look at and prove these theorems: orthogonality and 0. 0 is orthogonal to every vector in V, and 0 is the only vector in V that is orthogonal to itself. The Pythagorean theorem: suppose u and v are orthogonal vectors in V, then the norm of u plus v is equal to the norm of u squared plus the norm of v squared. We will look at orthogonal decomposition, which you have most likely done in vector calculus. So suppose we have a vector u and v in our vector space with v not equal to 0. We want to write u then as a sum of two vectors, some scalar multiple of v plus some scalar multiple of a vector that is perpendicular to v. So we'll set c equal to the inner product of u and v divided by the norm of v squared, and then we'll find that w, that's going to be our perpendicular vector, will equal to u minus the inner product of uv divided by the norm of v squared times the vector v. Then the inner product of v and w is equal to 0, and u is equal to, this vector here, a linear combination of v and this new perpendicular vector w is equal to cv plus w. And again, the idea now is that we have decomposed our vector u into a scalar multiple of c plus some other vector that's perpendicular to v. One other note. In my previous video, I had this overview slide, but I was missing this angle bracket here, this one here. So if you copied the overview slide from the previous video, please do make sure you make that correction. These last two theorems come up all the time in proofs, especially when you want to establish an upper bound or lower bound. That's that greater than or equal to sign. So first we have the Cauchy-Schwarz inequality for vectors u and v. The magnitude of the inner product uv is less than or equal to the norm of u times the norm of v, with equality if and only if one of uv is a scalar multiple of the other. Then we have the triangle inequality. Suppose u and v are vectors, then the norm of u plus v is less than or equal to the norm of u plus the norm of v, with equality if and only if uv is a non-negative multiple of the other. So that concludes our overview slide. So let's go back, do a quick review of the things we did in our last video, and then continue on with norms and orthogonality. In our last video, because these complex conjugates kept coming up because we were doing proofs of different properties, we defined the complex conjugate if we have z is equal to x plus iy, the complex conjugate of z is equal to x minus iy. We have these properties of the complex conjugate. So if we have z, the complex conjugate of the complex conjugate, we just get back z. We also have the magnitude of the complex conjugate of z is equal to the magnitude of z. We have the complex conjugate of z1 plus z2 equal to the sum of the complex conjugate of z1 plus the complex conjugate of z2. Similarly for subtraction. And then we also have the complex conjugate of z1 times z2 is equal to the complex conjugate of z1 times the complex conjugate of z2, and a similar rule for division. We also talked about how this norm is equal to, we interpret that in R2 and R3 as the length of a vector, and the norm of a complex number, the absolute values are needed because we want the norm to be non-negative, and we want to think of the norm as the inner product of z with itself, as we could see over here when we were talking about R2 and R3. We define the dot product for Rn. So if we have a vector x in Rn, which has the coordinates x1, x2 up to xn, and our vector y with the coordinates y1, y2 up to yn, then x dot y is equal to the sum of the coordinate by coordinate multiplication. The properties of the dot product is the dot product is always greater than or equal to 0 for all x in Rn, and you can see if you dot it with itself, you're going to get a bunch of squared coordinates added together. So it's always greater than or equal to 0. And it's equal to 0 if and only if x is equal to 0. We also see that x dot y is equal to y dot x. And last, if we fix a vector y in Rn, then the mapping from Rn to R, that is, our dot product maps from Rn, and then we get a scalar in R, that sends x in Rn to x dot y is a linear mapping. And all these we talked about in greater detail in our last video. We then define the inner product, which is an abstraction of the dot product. An inner product on V is a function that takes a pair of vectors in our vector space to a number in our scalar field F. We denote that number, or the inner product, with these brackets. So this is the inner product of U and V. And the inner product has the following properties. Positivity. So the inner product of V with itself is always greater than or equal to 0, and it's equal to 0 if and only if V is equal to 0. So very similar to the first two properties. I'm just going to check them off over here of the dot product. Next, we have the additivity in the first slot. So the inner product of U plus V with W is equal to the inner product of U with W plus the inner product of V with W. And we also have homogeneity in the first slot. So the inner product of a scalar alpha times U with V is equal to, we take the scalar alpha out, times the inner product of UV. These two properties are the idea that this mapping is linear, so that's where that comes from. We have this additional property because now here the dot product concerned only real numbers, but now we're talking about a general inner product, so we're potentially looking at complex numbers as well. So we have this extra conjugate symmetry. So the inner product of UV is equal to the complex conjugate of the inner product of VU. We did some examples, which I'm not going to do in full, but I'm just going to give you a brief introduction to a couple of them. First, we talked about the dot product. So it's an inner product for Rn, but if we try to extend that to Fn, possibly complex numbers, we see that it fails conjugate symmetry. So in order to remedy this, we need some sort of analogous thing for dot product and Fn, and we use the Euclidean inner product defined below. So it's essentially the same thing as the dot product. We do an addition of component by component multiplication, except the second vector we use the coordinates complex conjugate. So we have that definition here. And I did this work in our last video and talked about it. I verified positivity, homogeneity. Actually, I verified all of these properties, but I have these two here for your reference in case you want to look, but I will not go over them. And also, because we're totally generalizing the idea of inner product for any kind of vector, we also looked at an inner product on the vector space of continuous real-valued functions, and this was important. These were real-valued functions on the interval -1 to 1, and we defined the inner product as the integral from -1 to 1 of our first function times our second function. We verified all the properties, actually. I have a couple of them here for your reference in case you wanted to look. But again, we're not going to go over it in detail in this video. It's all in the previous video. And one other note, if we wanted to get rid of the condition that we needed to be real valued, in order to satisfy conjugate symmetry, much like the Euclidean inner product before when we generalized the dot product to complex numbers, we have to take the complex conjugate of our second vector, that is our second function. And that we also verified in our last video, so I'll let you take a look at that at our last video if you're interested. We talked about the inner product space, which is simply a vector space along with an inner product defined on it. We used the properties of the inner product to prove these properties for an inner product space. First, if we fix a vector u from v, the function that takes another vector v to the inner product of v with u is a linear map from v to f. 2, the inner product of 0 with u is equal to the inner product of u with 0, which is equal to 0 for every vector u in v. The next one is this additivity, so the inner product of u with v plus w equals the inner product of u with v plus the inner product of u with w. And finally, this homogeneity, the inner product of u with the scalar a times v is equal to the complex conjugate of the scalar a times the inner product of u with v. So it's not exactly homogeneity, but close. To conclude our review, I'm going to note that because the complex conjugate is denoted with this bar over the vector, I had to drop the convention of separating my scalars from my vector by putting a bar over my vectors. At this point, you have to pick up from context or from explicit words what things are vectors, and then the bar are reserved for complex conjugate. We are ready to start discussing norms. For a vector v in our vector space, the norm, which we denote with these double bars, is defined as the square root of the inner product with itself. We have these properties of the norm, that the norm is equal to 0 if and only if v is equal to 0. We also know because the inner product of v with itself is always positive. And then the second property, that the norm of alpha times v is equal to the absolute value of alpha, the scalar, times the norm of v. Our first example of the norm involves the Euclidean inner product. So if we have a vector in Fn, so these are possibly complex numbers. So when we take the inner product of a complex vector w with a complex vector z, we do our component by component multiplication, except our second vector, we're multiplying by the complex conjugate. So we have w1 z1 complex conjugate plus w2 z2 complex conjugate up to wn zn complex conjugate. Because the norm is the inner product of a vector with itself, then I use the Euclidean inner product to take the norm of z. So I start with the inner product of z with itself, so I get z1 times z1 complex conjugate, z2 times z2 complex conjugate, up to zn times zn complex conjugate. And looking at this line here from our review of complex numbers, we have that the absolute value of a complex number z squared is equal to z times its complex conjugate, which is what we have here. So in other words, our Euclidean inner product of z with itself is equal to the magnitude of z squared, which is equal to the magnitude of z1 squared plus the magnitude of z2 squared up to magnitude of zn squared. Which then, because the norm is the square root of the inner product, we have the norm of z is the square root of z1 magnitude of z1 squared plus magnitude of z2 squared up to magnitude of zn squared. When we're in 2 dimensions or 3 dimensions, this is what we typically think of as length of a vector. For our next example, we're going to look at the space of continuous real-valued functions from -1 to 1, and we're going to define the inner product as the inner product of function f with g is equal to the integral from -1 to 1 f of x times g of x dx. Then taking the inner product of f with itself, we have the integral from -1 to 1 of f of x times f of x dx, which tells us then that the norm of f is equal to the square root of the integral -1 to 1 of f of x squared dx. And the norm has these two properties. The norm of v is equal to 0 if and only if v is equal to 0, and the norm of a scalar alpha times v is equal to the absolute value of the scalar alpha times the norm of v. Now we are ready to discuss orthogonality. So we say two vectors u and v in our vector space are called orthogonal if their inner product is equal to 0. In R2, in vector calculus, we found that the inner product of u with v is equal to the norm of u times the norm of v times cosine of theta. So if we wanted to know when this inner product was equal to 0, assuming that u and v are not 0, we would be looking to see where cosine of theta is 0. So cosine of theta is equal to 0 when theta is equal to 90 degrees. And hence, in this way, we equate orthogonality with being perpendicular at a 90-degree angle. You notice when I was talking in R2 about u and v, I said we're going to assume u and v are not equal to 0. But now we have this theorem to talk about orthogonality when we have a 0 vector. So first, 0 is orthogonal to every vector in V, and second, 0 is the only vector in V that is orthogonal to itself. The proof is fairly straightforward. The proof of A that the 0 vector is orthogonal to every vector in V comes directly from the properties of the product space that we had proved in our previous video, and it comes from part B and C, where we say the inner product of 0 with u is equal to 0 for every u in V, and the second part where the inner product of u with 0 is equal to 0 for every u in V. The proof of part B that 0 is the only vector in V that is orthogonal to itself comes directly from our properties of inner product. This second property here that says the inner product of V with itself is equal to 0 if and only if V equals 0. The last part of our video will concern the Pythagorean theorem, orthogonal decomposition, the Cauchy-Schwarz inequality, and the triangle inequality. Many of these are proofs. We are going to start with orthogonal decomposition, and the idea here is if we have two vectors, u and v, in our vector space V, with v not equal to 0, we want to write u as a scalar multiple of v plus a vector w that is orthogonal to v. And the picture looks like this. We're given the vector u and the vector v. Now we want to write u as a linear combination of some scalar multiple of v and a vector perpendicular to w. This theorem tells us that c will be equal to the inner product of u and v divided by the norm of v squared, and that w then will be equal to u minus the inner product of u and v divided by the norm of v squared times v. So we'll develop this formula here. So we want to write an equation with u as a scalar multiple of v, and just so we have equality, we're going to say that's equal to u minus cv, right? So these cv's cancel and we're left with u. So this is an equation that certainly is true, and we want c now to be such that cv over here is perpendicular to this u minus cv, and that will give us u as a linear combination of v and a vector that is perpendicular to v. So in other words, we want this u minus zv to be perpendicular to v. So the inner product then will equal to 0. By my additivity in the first lot and homogeneity in the first lot, my properties of inner products, I can rewrite this inner product as the inner product of u with v minus c times the inner product of v with v. Here, our inner product of v with v, that's simply the norm of v squared. So now we can rewrite c as equal to, well, moving c over to the other side and then dividing both sides by norm of v squared, we get c is equal to the inner product of uv divided by norm of v squared. And now we can write out our u is equal to plugging in c times v plus u minus, now we plug in again c times our vector v. So this is our formula of u as a linear combination of v. You can see that this is going to be a scalar multiple of v plus another vector u minus another scalar multiple of v. Our next proof will be of the Pythagorean theorem. So suppose u and v are orthogonal vectors, then the norm of u plus v is equal to the norm of u squared plus the norm of v squared. I'm going to start with the left-hand side of this equation, and I'm going to square it. So I have the norm of u plus v squared, and by definition of norm, that's equal to the inner product of u plus v with itself. And now by additivity in the first lot, this is equal to the inner product of u with u plus v plus the inner product of v with u plus v. By conjugate symmetry, this is equal to the complex conjugate of the inner product of u plus v with u plus the complex conjugate of the inner product of u plus v with v. From there, by additivity on the first lot, this vector here becomes the complex conjugate of u with u plus the complex conjugate of v with u. By conjugate symmetry, we can flip the order of these two, take the complex conjugate, and we get the inner product of u with u. Over here, we flip the order and take the complex conjugate, so we get the inner product of u with v, and we still have this term over here, the inner product of, or the complex conjugate of the inner product of u plus v with v. So we'll work on this next. And we're using additivity on the first lot, so now we're going to have the complex conjugate of the inner product of u with v plus the complex conjugate of the inner product of v with v. Again, using conjugate symmetry to get rid of these complex conjugate bars. So we're going to flip the order and we get the inner product of v with u. Over here, we still have the inner product of v with v. We can now use our definition of norm to simplify the inner product of u with u as the norm squared plus inner product of u with v plus the inner product of v with u plus, again here using the definition of norm, the norm of v squared. Now because u and v, remember, they are orthogonal. So the inner product of u and v and the inner product of v with u, these are both 0. They're going to go to 0 because they're orthogonal. So what we have then is the norm of u squared plus the norm of v squared, which then concludes our proof of the Pythagorean theorem. Our next proof is of the Cauchy-Schwarz inequality. If u and v are vectors in v, then the magnitude of the inner product of uv is less than or equal to the norm of u times the norm of v, with equality if and only if one of uv is a scalar multiple of the other. We will start with the case when the vector v is equal to 0, and then later move on to the case where the vector v is not equal to 0. So for v is equal to 0, then the inner product of u and v, well, the inner product of u, or any vector with 0, is equal to 0. So the absolute value will be equal to 0, and we have that is equal to the norm of u times the norm of v. For the case where v is not equal to 0, we'll consider the orthogonal decomposition where u is equal to a scalar multiple times v plus w, where w is perpendicular to v. we're going to have this picture here from our orthogonal decomposition. We have our vector u, our vector v. We're decomposing u as a linear combination of v and w perpendicular to v. But now because v and w are perpendicular, we can apply the Pythagorean theorem. So the norm of u squared is going to equal to the norm of our u squared plus norm of our w squared. We can simplify this a little. So on top, we're going to have the absolute value of uv, and then we have the squared. And this v, since the norm of v is equal to the square root of inner product of v with v, which is the norm of v, this v squared will cancel with one of these v squared terms, and we'll be left with norm of v squared plus the norm of w squared. And since this norm of w squared is always positive, that means this sum here is greater than or equal to just this one term, which is the absolute value of the inner product uv squared over the norm of v squared. I can multiply both sides of my equation by norm of v squared, and then taking the square root of both sides, I get my Cauchy-Schwarz inequality, which is the norm of u times the norm of v is greater than or equal to the absolute value of the inner product of u with v. If we interpret this here, the absolute value of the inner product of u and v as the Euclidean inner product, then what we get is this interpretation: the length of each side of a triangle is less than the sum of the lengths of the other two sides. We'll do an example to illustrate that next. I cleared out some space, put my Cauchy-Schwarz inequality here, and our example is if we have a list of scalars, so x1, x2 up to xn, and scalars y1, y2 up to yn. These are real numbers here. Then we can show that the magnitude or the absolute value of x1 times y1 plus x2 times y2 up to xn times yn is less than or equal to our x1 squared, x2 squared up to xn squared times y1 squared, y2 squared up to yn squared. Notice in this example problem, as it's presented, it does not say that these x values are part of a vector or these n y values are part of a vector. They just say we have n real numbers that we designate x1, x2 up to xn, and then another list of real numbers that we designate y1, y2 up to yn, and we want to show that this inequality holds. Of course, the trick is we're going to interpret these as vectors and then invoke things that we know from orthogonality of vectors and inner products. So we start with interpreting the first n real numbers as a vector x, and the second set of real numbers as a vector y in Rn. That will allow us to look at the absolute value of the inner product. So we have our inner product, x1, y1 plus x2, y2 up to xn, yn, and we take the absolute value. Now by Cauchy-Schwarz, the absolute value of this inner product should be less than or equal to the norm of our vector x and our vector y. So less than or equal to the norm of x, the norm of y, but the norm of x as a vector is equal to our x1 squared plus x2 squared up to xn squared, and then the norm of y as a vector is y1 squared plus y2 squared up to yn squared. And hence we have proven our statement here. Our next example, if f and g are continuous real-valued functions on -1 to 1, then we want to show this statement here, that the absolute value of the integral from -1 to 1 of f of x g of x dx squared is less than or equal to the integral from -1 to 1 f of x squared dx times the integral from -1 to 1 g of x squared dx. And similar to this problem, at this point we haven't really talked about f and g as being vectors in the space of continuous functions, but we can certainly interpret them that way, and then we can bring in our normal, no pun intended, our definitions of orthogonality, our properties, in order to prove this inequality. So we start with using then our inner product of f of g defined as the integral from -1 to 1 f of x g of x dx. And again, this is for real valued functions, and this is from a previous example. We can then invoke Cauchy-Schwarz and say the absolute value of the inner product is going to be less than or equal to the norm of f times the norm of g. So the absolute value of our inner product is the absolute value of the integral from -1 to 1 f of x times g of x dx, and the norm of f times norm of g is going to be the integral from -1 to 1 f of x squared dx, and then the norm of g of x is the integral from -1 to 1 g of x squared dx. There should be a dx. And hence, we have interpreted these functions as vectors in this vector field of continuous functions. We then used our definition of inner product for real valued functions and the Cauchy-Schwarz inequality to prove this inequality here. Finally, we will prove the triangle inequality. Suppose we have u and v vectors in our vector space V, then the norm of u plus v is less than or equal to the norm of u plus the norm of v. We have equality if and only if one of u or v is a non-negative multiple of the other. And I just rewrote my inequality. I start with taking the square of the left-hand side. This looks a lot like the other inequality we proved, the Pythagorean theorem. So I take the square of the norm of u plus v, and that's equal to then the inner product of u plus v with itself. And as I said, this proof is really similar to the proof of the Pythagorean theorem. In fact, we're going to borrow all these steps from the Pythagorean theorem to show that this inner product of u plus v with itself is equal to the inner product of u with itself plus inner product of u and v plus the inner product of v and u plus the inner product of v with itself. And again, I'm not going over all these steps because we did them in the Pythagorean theorem. You can look back at your notes. So I'm going to group my inner product of u with u, my inner product of v with v. I have my inner product of u with v plus my inner product of v with u, but I'm going to use conjugate symmetry to reverse the order and put the complex conjugate of inner product of u and v. At this point in our Pythagorean theorem, u and v were orthogonal, so these two inner products went to 0. We don't have that here in our triangle inequality. Now, our inner product of u with itself is the norm of u squared, inner product of v with itself is norm of v squared, and we still have inner product of u and v plus the complex conjugate of the inner product of u with v. And now we're going to use the fact that we have the inner product of uv plus the complex conjugate of the inner product of uv. So in general, if you have a complex number like a plus bi and add it to its complex conjugate, the bi's are going to go away and you're going to be left with 2a. So over here, these two inner products summed together is going to give us the real part, twice the real part of the inner product of uv. Now the absolute value of the inner product of uv is equal to the absolute value of the real part of uv plus the absolute value of the imaginary part of uv. In this case, we don't have an imaginary part, so this is equal to 2 times the absolute value of the inner product uv, which is less than equal to the norm of u squared plus norm of u squared plus twice norm of u, norm of v. This part here comes from Cauchy-Schwarz. And then finally, we get that's equal to the norm of u plus norm of v squared. And hence we have proved the triangle inequality. To review what we have covered in this video, this is the second of 2 videos that cover inner products and norms. We did a very brief review of the stuff we covered in our first video, which was dot products, inner product, and inner product spaces. Then we went on to cover norms and orthogonality. So for norms, we defined the norm of a vector v in a vector space V as the norm is equal to the square root of the inner product of v with itself. We had these properties of the norm, that the norm of v is equal to 0 if and only if v is the 0 vector, and b, that the norm of a scalar alpha times a vector v is equal to the absolute value of alpha times the norm of v. We talked about orthogonality of two vectors, u and v, in our vector space. So u and v are called orthogonal if the inner product of u and v is equal to 0. And from vector calculus, we discussed orthogonality, and R2, we defined the inner product of u, v was equal to the norm of u times the norm of v times cosine of theta. So if we wanted to know when u and v were orthogonal, we would take the inner product and look to see if it was equal to 0. And essentially, we would look to see where it's equal to 0 because this norm of u, norm of v cosine theta, if u and v are not equal to the 0 vector, then that would have to mean that cosine of theta is equal to 0, and cosine of theta is equal to 0 when theta is equal to 90. In that regard, we consider being orthogonal equivalent to being perpendicular. We had this theorem here concerning the 0 vector. You notice over here I had said we're going to assume u and v are not 0. Well, what if u or v is equal to 0? Well, if we have the 0 vector, then it's orthogonal to every other vector in the vector space. And the 0 vector is also the only vector in v that is orthogonal to itself. Finally, we had these last four theorems considering the Pythagorean theorem. Suppose u and v are orthogonal vectors in v, then the norm of u plus v is equal to the norm of u squared plus the norm of v squared. We had orthogonal decomposition, where our goal was to write a vector u as a linear combination of v plus another vector that was orthogonal to v. So suppose we had vectors u and v in a vector space with v not equal to 0. Then we would set c, our scalar multiple of v, equal to the inner product of uv divided by the norm of v squared, and then w, our vector perpendicular to v, would be equal to u minus the inner product of uv divided by the norm of v squared times our vector v. And hence, u would be equal to cv plus w. And also, w is perpendicular to v. Our next theorem was the Cauchy-Schwarz inequality for two vectors u, v in our vector space. Then the magnitude of the inner product of u, v is less than or equal to the norm of u times the norm of v, with equality if and only if one of u or v is a scalar multiple of the other. And finally, we did the triangle inequality. Suppose u and v are vectors in v, then the norm of u plus v is less than or equal to the norm of u plus the norm of v. And there's equality if and only if uv is a non-negative multiple of the other. And that's it for our video. Thank you for watching.